I will talk more about topology, I guess, than algebra in this talk. And I also want to sort of give a very rough preview before I even start. So for the first many slides, I will actually reveal sort of what we know about topology and what we know about tropical wildlife and tell a story that leads up to our research. And because we work with some combinatorial objects that are rather complicated, and I think I would like to give enough motivation for you to care about these complicated combinatorial objects. And so we'll start with some history and some known results and some successful stories that we built on. And this is joint work with Yasin El-Masous, Paul Helming, Billy Tula, and Pico Suso, who's in the audience. And so let's start. So we'll quickly do some history of what we know about the cohomology of MG. So MG is a moduli space of smooth curves, as in classes of smooth curves, and it is a very central object in modern algebraic geometry. And one aspect of it that is quite mysterious is its cohomology. And so projective curves logically are Riemann surfaces. And so to Riemann, it was already known that this moduli space has dimensions 3g minus 3 or real dimension 6g minus 6. And so that already tells us, like, for example, at which point the cohomology would stop. And in the 80s, Herrera and collaborators studied or discovered a bunch of exciting properties of cohomology. One thing we know is that if we look at the degree cohomology of MG, then if G is large compared to K, that cohomology is actually independent of G. And so as we increase G, then the bottom part of the cohomology stops changing at some point. And on the other hand, so due to Riemann, we know that when cohomology degree is above 6g minus 6, you will see 0. However, it actually stops before that. And Herrera also showed that when k is greater than 4g minus 5, we stop seeing cohomology. So right now we have the lower part of the cohomology doesn't change when G is large enough, and then the upper part becomes 0. However, Herrera and Xavier showed that the Euler characteristic grows more than exponentially as G grows. And so now this is sort of a problem, sort of a feature, right? Because we know the lower part and we know the higher part, and both of them are not growing, like they're constant with respect to G. However, there's some part in the middle of for the cohomology degrees that are clearly growing more than exponentially, because otherwise we wouldn't. The Euler characteristic is an alternating sum of dimensions of different degrees of cohomology. And so without some cohomology degree that's growing more than exponentially, we wouldn't see this fast growth in the Euler characteristic. And so then the question is, can we find a degree in which we actually see that this particular degree is growing exponentially with respect to G? And so it turned out to be not so easy to find this cohomology degree. And many decades passed, and a tropical approach was able to provide an example for such fast growing cohomology. So this is a theorem by Chan, Goethe, Spain from 21, where they showed that the dimension of the 4g minus 6 cohomology of MG is growing exponentially, or more than exponentially, I guess. And how is this tropical? Well, a very, very rough proof sketch starts with a cellular complex that we call a moduli space tropical curves. And this is a combinatorial object that has a CW complex structure. And on the other hand, a series of studies starting from Deline and then by Abramovich, Caprasso, Payne, and finally to Goethe's Payne showed that so there's a stronger statement than this, but this is what we mean, sort of, that this is our tropical space, delta G, and the homology, the rational homology of the cellular complex actually injects into the cohomology of MG. And now finally, they showed that the correct or a homological degree of the cellular complex has the desired dimension. And so now if we have this injection, then we know, right, the cohomology has to have a larger dimension than the homology of the tropical space. And so now the idea is that instead of studying this complicated algebraic object, we can transfer to studying a cellular structure and show its homology grows fast enough. And so that is the story our group wanted to copy, because it seems like a successful story and has interesting combinatorics. And so, but before we get into what objects that we work with exactly, I'll tell you about how this strategy is defined, because our story is pretty parallel to the steps in this moduli space of couple groups. So let's go back to MG and start with a compactification of MG. So MG comprises isomorphism classes of curves, and it is not compact. And so a famous compactification by Deline and Mumford adds to the boundary of MG nodal singular curves. And a curve is nodal if the singularities locally look like the origin, right, in the XY plane. And if we have a nodal singular curve, then it is stable. So this was also mentioned yesterday by Francesca. It is stable if we look at each component of this singular curve, and we see only finitely automorphisms. And specifically, what that translates to is that if we have a genus 0 component, right, then it's a Riemann surface. And what do we need to have finitely many automorphisms? We need to fix 3 points. And so we need 3 special points on that component, and it can be marked points or it can be the singular point. And now, if we have a component that is a torus, then we only need to fix 1 point for the torus to have a finite automorphism group. And so that's for that. And if we have more than genus 2, then we don't, it already has finite automorphism group, so we don't need to fix it. And so this relationship or these conditions can be summarized by requiring 2g minus 2 plus n, so n is the number of fixed points. I included here, although later we actually won't work with marked points. But we require this to be positive to have stability. And now that is the algebraic side of the story. How do we translate from algebra to combinatorics? So given a stable nodal singular curve, we can associate to it something called a dual graph. And what we do is that we will look at irreducible components of our nodal singular curve, and to every component, we assign a vertex. And now, for every node, right, node is when we see 2 components meet. And now on the graph side, we add an edge the two nodes that represent the two irreducible components if they meet at a singular point. And marked points, so for now I still have marked points, and marked points, they will become marked rays that come out of my vertices. And now finally, my components, they could have geometric genus. And so that genus becomes an integer weight that is assigned to a vertex. And so for this example, if I have two components, irreducible components, one is a torus and the other is P1, then now, well, actually, sorry. So this is, both of them are P1, and this component has a self-intersection, and this component has two mark points on it, and the dual graph will have two vertices for the two components, and the left one, oh, that's a typo. So this shouldn't have genus 0 because it's really a P1 with self-intersection. And so for self-intersection, we have a self-loop on the graph side, and the two of them are joined by one edge which corresponds to this node. And the two marked rays, they correspond to the two marked points. And so now we can actually look at the boundary strata of M2, where we look at some Riemann surface with genus 2 and look at different ways we can degenerate in the boundary. And by degeneration, intuitively, what we do is we take an S1 on our two-handled body, and then we shrink it to 0, or we shrink it to a point. And so this is the kind of like the open part of M2. This is like the Riemann surface for a curve in in M2, and we have two choices of S1 to degenerate. So if we pinch together this S1 in the middle, then we end up having a singular curve with two genus 1 components, or we can pinch a circle around one of the handles, then we end up with a torus but has a self-intersection. And so we can do this game and keep shrinking down S1s until we have a bunch of P1s that are intersecting each other or themselves in various ways. And it turns out, so this is kind of like the big open in M2 bar, and we have 6 different boundary strata. And on the dual graph side, what we have, so this is flipped, where this vertex with weight 2, that corresponds to the big open part. And then as we go up, then we see more and more edges, and we also see a decrease in vertex weight, because if we still have vertex weight, then that means we can pinch more circles. So now, based on our dual graph description, let's define an abstract tropical curve. So these tropical curves, they don't look like the tripod because they are coordinate free. And for an abstract tropical curve, now we define it to be a graph that has, so we start with a finite connecting graph where parallel edges and self loops are allowed. And we have a number of decorations on this graph. And one decoration is this weight assignment that tells us the genus of each component. And we have a marking assignment that tells us if there are marked points, which component they live on. And we also have an edge length function that assigns to every edge a positive real number. And this part I did not mention too closely, but the edge length corresponds to something called the speed of degeneration. It's basically like how fast we're shrinking down the S1 into a point. And the stability condition that we mentioned earlier translates to this following expression where we look at twice the weight of a vertex, and we add to it the graph theoretical degrees of how many edges, how many half edges are coming out of my vertex. And if I have marked points, then I also add the marked points. And I require this value to be at least 3. And this corresponds to the idea that, so the degree, right, that corresponds to how many singular points or how many nodes we see on a component. And then this marked points, that's marked points. And so we need at least 3 for genus 0, and we need at least 1 for genus 1, etc. And we also define the genus of an abstract tropical curve of this graph to be the graph theoretical genus. So that's like the first steady member of the graph. But we should also keep track of the genus of the components that are hidden. And so we also add to it the vertex weights. So now we define tropical curves, and let's define the moduli space of tropical curves. Instead of giving you a precise definition, I think I'll do it with an example because it's much easier this way. So as I promised, the tropical spaces are cellular structures. And so I will start by giving you the cells. And the cells correspond to combinatorial types of these dual graphs. And as I mentioned earlier, for each combinatorial type, the edges come with edge lengths. And so if I fix a particular combinatorial type, then I can count how many edges there are, and they give me sort of like a quadrant in R to the number of edges. And I will immediately define a normalized version of this also to help with my drawing. So I actually require my edge lengths to add up to 1. So instead of an open quadrant or an open cone, I actually get a simplex out of each combinatorial type. And so in particular, if I look at this combinatorial type, then I have 3 edges whose lengths add up to 1, and so that gives me a 2 simplex. And similarly, for this theta graph, I also get a simplex. And the other ones, I'll have an edge and point correspondingly. And now I give you the cells, I should tell you how to glue them together, how to assemble them into a moduli space. And what we do is that there are 2 conditions for gluing that we have to follow. The first one is on the boundary, when a particular edge has edge lengths going to 0, I identify that boundary with contracting that edge graphs directly. And so let's say I have let's say this is one. So this edge corresponds to when C goes to 0, and now I identify that with contracting this loop. And maybe I didn't mention, but when we contract the loop, we'll increase the vertex by weight 1 because algebraically what we're doing, right, is to shrink an S1 on the torus down to a point. And so this part will become, so C0 is identified with this graph. And so that's condition number 1 of how we glue. And condition number 2 is we also glue, we also identify these simplices by automorphisms, meaning that if I see an automorphism on my graph, then I will portion out by this identification on the simplex as well. And so what that, how that works in the example is that here I have an automorphism swapping A and C, or swapping this entire graph, flipping it. And so instead of having this full 2 simplex, I only get half of it, where I guess I'll take this function. Because the other side will just be identified to this side via this automorphism. And so together, oh, so I should tell you what this one is. And this has a full S3 automorphism because I can swap these 3 edges however I want. And so on the simplex side, I actually only get 1/6 of my triangle. And so putting everything together, what we end up with so this would be delta 2, which is the normalized version of n top 2, and it looks like a half triangle together with 1/6 of the triangle. Yeah, question.
So it doesn't matter for your simplex, but do you consider swapping the vertices of the theta graph in automorphism?
No, because the simplex is tracking the edge lengths.
Yeah,
right? And so if I swap the 2 vertices, I mean, it is an automorphism, but it doesn't affect the simplex because the edge lengths, they are not affected by it. Yeah. And so delta 2, I have this half triangle with 1/6 of the triangle, and I have this graph here, and the theta graph here. And let's see. And in the normalized version, we never see this cone point, and that is okay. Yeah. Great. And so now to find this tropical moduli space, or moduli space of tropical curves, let's see why it's okay to call it tropical moduli space of curves. So as we mentioned, MGN bar is the Dewey-Mumford compactification by stable curves, and this is a very nice compactification because the open moduli space sits in it as a toroidal embedding and words. But what it means, what's important is that this complex, this cellular complex we just defined, is canonically identified with the boundary complex of this compactification. And what that means is that there's a one-to-one correspondence between the cells in this moduli, in this cellular complex with boundary strata, and they have matching automorphisms. And that leads to an isomorphism between the homology of the cellular structure with so this is a okay. So we have the cohomology of MGN, and it has some canonical weight filtration on it coming from a mixed Hodge structure. And so when we have this filtration, so it's a sequence of Q vector spaces, basically, we can look at the associated gradient. And so this homology is actually identified or isomorphic to the top piece of the associated gradient vector space in this filtration. And so that's why we end up getting an injection into the cohomology on the right side. Okay, so that's the successful story of MGN, where we can associate to it a cellular structure and then study the cohomology of MGN via studying the homology of WGN. And as we saw in the title, we want to study covers of curves. And so I will start with Hurwitz spaces, which parameterize covers, although very soon I'll specialize to the locus in Hurwitz space that we actually study. And so the Hurwitz moduli space parameterizes covers with a bunch of data associated to it. And so it parameterizes ramified covers, and the data we need to give include the genus of the target curve, the genus of the source curve, and we have some ramification data. That's when we don't. That's a finitely many points downstairs, where upstairs we don't see a topological cover of a fixed degree. And so in this case, this is sort of a cartoon of what might happen, where we have a degree 3 cover of a genus 0 curve. And I have 2 points over which I don't see 3 pre-images. And so there's something called ramification profile, and that tells me if I look at these points where I don't see a degree 3 topological cover, how are the sheets coming together? And it turns out that when I specify all these data, the genus of downstairs curve, the genus of upstairs curve, and these ramification profiles, they need to satisfy something called the Riemann-Hurwitz condition for such thing to even be possible to exist. And the Riemann-Hurwitz condition says, if I look at, so this is the genus of upstairs, and this is the genus downstairs, and D is the degree. And these ramification orders, they are just, if I look at these points where it fails to be a degree 3 cover, how many sheets are coming together? So this ramification point would have order 2, and this ramification point would have order 3. And so I can plug in all these numbers and check that this cartoon I draw, whether it's possible or not. And then I see that, okay, so I don't really know what's the genus on top, but I do know that the thing I'm covering is genus 0. And so I plug in all the numbers, and you see 2 ramification points. I have ramification order 2 and 3, so then I get 1 and 2 after subtracting 1. And I see that for this to work, the genus of my cover needs to be -1/2, which clearly is not possible. So that tells me that this cartoon I draw is just not possible. And now, similarly as before, to build a topolization, to build an abstract topolization, we need a suitable compactification of our moduli space. And in the Hurwitz case, there is a nice toroidal compactification, which is by admissible covers. And the idea of admissible covers is quite intuitive. It says if I have a cover, then I want to degenerate them at the same time. And so the nodes should go to nodes, the ramification points should go to ramification points, and I shouldn't shrink any components. And so basically, everything you want to happen, it should happen. And so dually, on the tropical side, what we're looking at is now a map of tropical curves where it is a graph morphism. However, if we look at a graph morphism, it's not always corresponding to a covering map. So it turns out that when we topolize a covering map, then the corresponding graph morphism satisfies something called a harmonicity. And how it's defined is that if we start with a morphism of metric graphs, then we can define something called a dilation factor. It's also called expansion factor in some literature. And that is, if I look at an edge down, okay. So if I look at an edge upstairs and it has a length, and I map it downstairs, it has some other length. And so I take the ratio, and that's going to be my dilation factor. And now this dilation factor sort of plays the role of this ramification. And harmonicity is a condition that says, if I focus on any vertex and I look at the edges around it, then I can look upstairs and see what are the pre-images. Then no matter which edge I choose, if I look at its pre-images and add up the dilation factors of all the pre-images, then it should be a fixed number. And that fixed number is also called the local degree. Because really what we're looking here is some cover. So this would be a genus 0 cover of some genus 0 curve, right? Because these vertices, they are really corresponding to components of curves. And so the definition of a tropical Hurwitz cover is therefore a graph theoretical morphism that satisfies harmonicity and it satisfies the local Riemann-Hurwitz condition. Because, like I said, when we look at locally around vertices, right, then we really see covers of actual curves. And we know that the Riemann-Hurwitz condition tells us when the cover is impossible. So it doesn't tell us when something is possible, but it does tell us when something is completely infeasible. And so we need the Riemann-Hurwitz condition to be satisfied locally for it to even be considered. And the local Riemann-Hurwitz condition translates to, I see that this is a little flipped before I had 2g minus 2, but this is taking the negative on both sides of the condition before. We have 2 minus 2g of a vertex upstairs, and then this d of v prime is this local degree that we just defined, and then these d of e prime, they are the dilation factors upstairs if we look at the edges. And so here is an example of what might happen. So this is a degree 3 cover of a genus 2 curve. And I have this loop mapping just down to this loop and the other one too. But in the middle, I have 3 edges covering this one edge in the middle. And so by definition, the dilation factor, well, I guess for now, I can tell you what dilation factor I want. And so I'm going to assign 3 for the loops and 1 for the 3 edges in the middle. And so I can check whether harmonicity is satisfied. So if I focus on this vertex, then I see, or focus on v and v prime, then I can take one of the 3 half edges coming out of v. And if I pick this horizontal edge, I see 3 pre-images, each with dilation 1. So I add them, and that number is 3. But now if I take one of these 2 half edges in the loop, I only see 1 pre-image upstairs, but the dilation factor is 3. And so it's the same number, which means harmonicity is satisfied, and the local degree is indeed 3. And we can also check that Riemann-Hurwitz, the local Riemann-Hurwitz is satisfied. And this condition will usually tell us what genus. So if we fix a curve downstairs, that will usually tell us, dictate what's the genus or what's the weight of its preimage or its preimages. And in this example, I have weight 0 for all the vertices. And so I can check that local Riemann-Horowitz works out, and I don't get any contradiction. Okay, so this seems very nice and parallel to what we were discussing before. We have covers and we tropicalize them. And can we build a moduli space just like before? And the answer is yes. So we can construct a tropical Hurwitz space or moduli space of tropical Hurwitz covers by a similar construction where we assign edge lengths and for each combinatorial type associated cell and then glue them together via this edge contraction and automorphism properties. And it was also a successful story, and two groups, Bertrand, Bugali, and Matakan, and the other group, Cavalier, Marquich, and Regnaton, they were able to show that classical and tropical Hurwitz numbers coincide using this technique. So these Hurwitz numbers, they are counting how many covers there are when the moduli space has dimension 0. However, their enumeration problem was solved, or we see that enumeration on the tropical side and classical side are the same. But it turns out that topologically, the topological space actually doesn't really transfer because before, in the case of MGN, we have this very nice one-to-one correspondence between the cells and boundary strata with matching automorphisms. But in the case of this tropical Hurwitz space, we actually have a little mismatch between the strata and also with automorphisms. So it's not really a problem for enumeration because it is possible to attach multiplicities or weights to these counts to account for the overcounting or the how many automorphisms there are. But these weights would not help when we look at topological information. And so what we are looking for is some space where when we compactify it, we don't get a mismatch between the algebraic boundary strata and combinatorial types, and we want automorphisms to also be well behaved. And so that leads us to a moduli space of covers with action from a group. So now, instead of just all Hurwitz covers, we're focusing on a subset of them that have some group action on the cover. And so now we have even more data associated, right? We have a Hurwitz cover, we fix some group and have a group action on the source so that now the covering map is actually a quotient map by this group action. And what is good about this particular locus? I think one obvious answer is that it turns out that it matches what we want. It has the nice property where if we look at its admissible covers on the boundary, then we do see this nice correspondence without missing or without overcounting or missing any strata. However, it is also not, I mean, on one hand, it is artificial, but on the other hand, we also include important cases like hyperelliptic and bielliptic curves. So these are degree 2 covers of curves. And when you have a degree 2 cover, then it always comes as an involution. And so then they would fit in the case when we take G to be Z mod 2Z. And so we do see some important cases that are part of like this construction. And we also have morphisms from this locus in the Hurwitz space to other MGNs. And so in this H space, we parameterize covers, right? Then we have a source graph and a target graph. And so it comes with two maps where if we take the source, then we get a map to one MGN with suitable G. And these are the ramification points that we remember. Or we can take the target curves, then that is another different genus, and then we remember the branch points. So those are the points on the target, which are images of ramification points.
So are you labeling them upstairs, or is there really a question? It's a different question.
Sorry,
are you labeling your ramification points?
Yeah, I am labeling them. Yeah, so upstairs, then I do label the replication points, and downstairs I label the branch points.
I'm just asking because you didn't put it in the definition.
Yes. So branch points and ramifications, they are all labeled. That is true. And so and these maps to MGN, they are also have nice properties. And I have to say, I'm not, I haven't looked at these maps too closely, and these I just took from the paper that defined the space. And so the source map is representable, finite, and ramified, and a locally complete intersection. And this target map is flat, proper, quasi-finite, and etal, but it is not always, not usually not representable. But I think the point is that we do get nice maps to MGN for various G and N, and therefore, hopefully, whatever information we extract here can be translated to MGN as well for a proper G and N. And so, for our project, we specialized in the case when the group action is coming from a cyclic group of prime order, because they are one of the simple groups, and both simple and like simple in the usual sense. And we also ask our covering map to be unramified to maximally simplify things. Yeah.
Feel free to refer me to the literature if you don't know this. How do you define, if you have an entire map between stacks, you usually define it in a way that any base change along to an actual space is entire. How do you define being entire if you're not representable?
That is a good question. I was reading the proof for that yesterday, and it is in the paper by Schmidt and Zalman. They discussed that.
Okay.
Yeah, but I don't know it on top of my head. Okay. Okay, so that leads us to the definition of tropical Z-mod PC cover. And as you can see, it has a lot of decorations, which is why I didn't want to start with this. I think it's hard to care about something that is so complicated if we don't know, why they're there. And so I'll quickly go through these conditions, but immediately introduce examples because then we actually see the commentaries. So I'd like to start with a graph morphism of metric graphs. And so nodes mapping to nodes, edges mapping to edges. And I need both of my graphs, source and target, to be stable. I need a G action on the source, and G is Z-mod PC. So I need a Z-mod PC action on the source such that this graph morphism is exactly the quotient set by that action. And I'm going to define my dilation factor as the size of the stabilizer. And it turns out that when I define dilation factors like this, then this graph morphism is automatically harmonic. And then I require my graph morphism to satisfy local Riemann-Hurwitz, which in fact will tell us, so if we start with a target, so downstairs curve, and if we define a degree, then, or if we know most of the data, then the local Riemann-Hurwitz will tell us what's the weight of vertices upstairs. And finally, I also need something called a monodromy data, which I didn't talk about much, but it is, and it's because I don't know much about it, but it's about when you have a ramification point or a marked point, then you can look locally like the, right, then locally it looks like a punctured plane, and then you can like go around it, and then there's something about how many ways you can go around your punctured point. But combinatorially, what we need is something called a dilation flow. So this happens downstairs. So this is some data on the downstairs graph. I assign group elements to the half edges downstairs such that it's 0 if I see an honest degree D topological cover upstairs. But now, if I do see dilation, which means that I don't have an honest degree D topological cover, then I will assign a non-zero element of my group. And they also need to satisfy that, well, if my two half edges are actually, partners in one edge, then I need their dilation data to match, to be negative of each other. And if I look at any vertex and add up the dilation data around that vertex, it needs to be 0, which is why it's called a flow, because you can actually view condition B as orienting your edges, and condition C as saying, well, the incoming amount needs to disperse into the outgoing edges. And so let's look at an example where it's the same degree 3 cover we saw earlier. And so downstairs, so we have this degree 2, genus 2 graph with 2 dumbbell with 2 ears. And then upstairs, I have 3 edges in the middle, and my Z-3 action on my source curve is to fix the 2 ears and permute the 3 edges in the middle cyclically. And now, so first I write down my dilation factors, and that's fixed by the Z-3 action on the upstairs curve. I write down stabilizer sizes, and I have 3 on the 2 sides because they're not changing by the Z-3 action, and I have 1 for those 3 edges in the middle because the only thing that fixes them is the identity. And then for the dilation flow, so what we need, right, is to assign 0 if we see an honest degree 3 topological cover. And so that's the edge in the middle. So the 2 half edges, they both get 0 because if I look upstairs, I just see 3 sheets. And the 2 loops, they get 1 and -1 for the 2 half edges. And it doesn't matter which side I put them because we can, because a loop, you can always flip it and it doesn't matter. And then we can verify harmonicity, right? That means if we focus on, for example, V1, then it's like the same harmonicity as before. I pick any half edge downstairs, look upstairs, add up the dilation factors of the three images, and we always get degree 3. And we can also check Riemann-Hurwitz, which also works in this case because we've done it before. This is the same example as before. And now let's look at a different example since there are like so many things to consider. So here I'm looking at a map covering itself, but now upstairs I still have a degree 3 cover, but I let my group act trivially without moving anything. And so then the dilation factor upstairs would be 3 everywhere, since that is the stabilizer size. And now the dilation flow, that is a data on the bottom, right? And then I can assign now non-zero elements to the half edges because I never see an honest degree 3 particle cover anywhere. So now all these dilation data needs to be, dilation flow data needs to be non-zero, and I choose to assign 1, 1, 1, and -1, -1, -1 on the other side. And then I do see, if I focus on V1, for example, and add up the elements around it, then I get 0. And harmonicity, now in this case, dictates that upstairs I need to see weight 1 on both vertices. And wait, sorry. So that's Riemann-Hurwitz. Harmonicity, again, we can check if we add up everything, then it's always 3. And then Riemann-Hurwitz tells us that upstairs we should assign weight 1 to the vertices. And so that is how the combinatorial types of these Hurwitz covers with cyclic group actions look like. And then what we can do is, like we did before, we assign edge lengths and then have these combinatorial types, these cells, and then glue them together via edge contractions and automorphisms. And this is how the moduli space of cyclic Hurwitz covers with cyclic actions look like when I have genus 2 for the target curve and the sigma 2 and the degree 2 cover. And now finally we get to our theorems. So we have 3 main theorems about the topology of these cellular complexes that are the moduli spaces of tropical Hurwitz covers with cyclic actions. And so the first theorem is about different subcomplexes in our cellular structure that are contractible. And so we define something, so this is called the weight locus, the loop weight locus, bridge locus, sparsely connected and parallel. And instead of giving you all the definitions, I will just draw them out in the example that I just did. So this is degree 2 covers of genus 2 curves. And then the weight locus is basically when we see a positive weight vertex on the bottom, and upstairs we also see the weight that is that is at least the degree times the downstairs weight, and so that gives us this yellow like edges, the 2 of them, and then loop weight is sort of corresponding to when we see a loop downstairs that has like p many copies of loops upstairs, and that's this pink part, and together with the weight locus. And then the bridge locus is when we see a bridge downstairs which lifts 2 bridges upstairs. So a bridge is an edge whose removal would disconnect the graph. And then we also have on this side the sparsely connected, and so that's when that's like harder to explain, but that's when we remove one edge downstairs and its images upstairs, and then we see the a component that becomes disconnected upstairs. And then finally, we also have the parallel locus, which is when we see a pair of parallel edges that are lifted also to parallel edges. And so in our case, I mean, of course, in this case, the whole thing is contractible, so it doesn't look very impressive. But then we see these are the, or this is the part that we understand. Okay, yeah. So in that case, I will not go through proof idea and move on to the next main theorem. So we also proved that delta GP. So this is not genus G with P mark points, but with Z-mod PZ action. Is simply connected for G at least 2 and P prime. And the basic idea is that we can look at so simply connected means that pi 1 is trivial. And so we can look at,
sorry, which locus was it?
So this is the entire moduli space. And we show that its pi 1 is trivial. And we rely on this theorem by Alcock-Torrey-Payne that tells us that pi 1 is generated by the one skeleton. And so that means that if we just look at the one skeleton, we can look at what cycles there are, and then we can look at the two skeletons, and if they're eliminated in the two skeletons, then we know that there cannot be further pi 1. And now our third theorem is that when we have P covers, Z-mod PZ covers of genus 2, then this moduli space is contractible if I have degree 2 or degree 3 covers. And now for further P covers, we actually see the homotopy type to be a wedge of spheres, where the number of 2 spheres is this value. And now, how did we come up with this? So the idea is that we listed top dimensional cells, and then based on theorem 1, right, we know a bunch of subcomplexes are contractible, and so we contract all those guys away, and it turns out that a bunch of these top dimensional simplices are also contractible. And so what happens is we have a number of 2 simplices that are not contractible themselves, but all their boundaries are contained in this big contractible subcomplex. And so once we contract them, we end up with these bubbles that are our 2 spheres. And then we only need to enumerate how many such non-contractible 2 like top cells there are, and then that turns out to be this number. And so far, I've mostly stayed on the combinatorial side, and by a theorem from Pedro, which hopefully will be on the archive like by the end of this week. That yeah, so did I say something wrong? So by a theorem by Pedro, we actually do have a rigor. So before I only gave you an intuition, right, for why our tropical covers are the way they're defined, but I didn't give you rigorous proofs, and that is because it's contained in this upcoming paper. And it tells us that indeed, we have a one-to-one correspondence between these combinatorial types and boundary strata, and all the algebra and geometric things work out. And so we actually do have the same identification of the rational homology of the cellular complex with this top weight rational cohomology. And so with this theorem, we can actually translate what we know about the homology of our cellular complex into this algebraic moduli space. And so I think I'll end it here. Thank you very much.